Thank you for joining our 6th GMDSI webinar, which is focusing on PEST++ and PyEMU. I'm Catherine Moore and I work at GNS Science in New Zealand, and I'm part of the GMDSI team that's organising this webinar series. I'm really happy to introduce Jeremy White and Mike Fienen in this webinar. At GNS, we were really lucky to have Jeremy working with us for a couple of years until he returned to the States last year. And we also had the pleasure of working with Mike Fienen over a summer visit to New Zealand. Jeremy and Mike are distinguished for a number of reasons, including the focus of today's webinar, as they lead the development of PEST++ and PyEMU software tools. These tools are compatible with PEST and they continue the PEST modelling approach, and that has the result that the entire way that groundwater modelling is routinely done around the world is changing for the better. Finally, I should point out that this webinar is on the technical side and it's designed primarily for modelers. And I should also point out that the following two webinars will be less technical. The first focusing on the geologist-modeler interface, and the second will show a series of decision support modelling outputs from a number of real-world worked examples. Having said that, there are also real gems that non-modelers can take away from this webinar on PEST++ and PyEMU. At the end of the webinar, you're welcome to ask questions of Jeremy and Mike, but also feel free to type questions during the webinar in the Q&A box on your screens. And if possible, can you write those questions in the Q&A box rather than chat box to make sure that we see your questions. And so with that, I'll hand you over to Jeremy and Mike to show us the magic.
All right, thanks for that, Kath. So I'm Jeremy White, and in this webinar, Mike Fienen and I are going to talk to you about some of the current capabilities in PEST++ and PyEMU. First, I want to acknowledge the GMDSI project. It's a phenomenal effort underway. They have a great website with more and more resources being added almost daily, it seems, so I encourage you to keep checking back at that website and stay current. I also want to acknowledge all the present and past contributors to both PEST++ and PyEMU, a great group of folks here. And if you're looking to join us, we're always accepting new contributors. So in this webinar, Mike and I are going to switch hit a little bit between PEST++ and PyEMU. I'm going to cover PEST++, he'll cover PyEMU, and we'll go through some basic sort of high-level design philosophy things behind these tools, and then we'll go through a few worked examples. So why do we need tools like PEST and PEST++? Well, it really comes down to the difference between predictive modeling versus explanatory modeling. In decision support, we're really interested in predictive modeling, and in that context, the ability to quantify uncertainty in the important simulated outcomes, as well as reduce that uncertainty through data assimilation, are just as important as the forward model. But given the wide range of settings that these groundwater models and environmental models are being applied in, and the various scales and processes that work in those settings, we need UQ and DA tools that can work across all those different settings. And so that's where PEST and PEST++ really come in, because they are model independent, model agnostic, and the algorithms in those tools are designed to work at real world scales. And so John and Kath have laid, again, the theory and concepts related to this topic out in previous webinars. Executable. You can build it for PC, Linux, and Mac. Every tool has both a serial and parallel run manager. We'll talk about that more in a minute. And then if you're on the Windows side of things and you want to get started, there's a Visual Studio solution that comes with PEST++. And so you can use the free Visual Studio and the free Microsoft C compiler to actually get started and do some pretty exciting things with that IDE. So currently, we have global sensitivity analyses in PEST++, and that's for screening, diagnostics, checking the plumbing. Of course, there's data assimilation and uncertainty analysis. There's management optimization under uncertainty. And then there's a tool for just generic parallel run management for design of experiments, emulator training. Basically, if you have a batch of runs you need to get done in the PEST world, this tool will help you do it in parallel and with some CSV files. So if you want to get the codes and documentation and support, it's all on GitHub. That's where we have the precompiled binaries. That's where we have the source code, the user's manual. We encourage people to use GitHub issues for support. So if you have a feature request or a bug report, or you just want to complain about PEST++, that's the place to do it. There's also a USGS version 5 report that myself, Randy, Mike, and John have authored. It's still in press. I'm not going to talk about why. I'm going to stay positive tonight, but it'll be released very soon. So here's what the GitHub page looks like. And like I said, here's where you can open an issue if something's wrong. The user's manual lives in documentation. I want to thank John for getting that off the ground. That was a huge effort, and it's been really nice to have a user's manual. That user's manual is actually in Word format. So if you're looking at that and there's something you think isn't clear enough or could be explained better, we encourage you to make those modifications and submit that as a pull request so that everyone can benefit from your insights. The source code, of course, is on GitHub, and then those binaries are over here under releases. So like John has talked about before in previous webinars, run management is fundamental to these decision support analyses. And that's because we're going to have to run the model many times. And so all the PEST++ tools have both a serial and a parallel run manager. The serial run manager is kind of boring. It does the model one at a time. And it misses out on that parallelism that exists in these decision support algorithms, because every single one of the model runs we have to do is independent of all the others. So we can exploit that parallelism with the master worker concept, just like PEST HP and BayoPest. So from a user perspective, it works just the same. The master sends out a run to a worker. The worker executes that run, sends back some results. That happens through TCP. You start master and worker just the same as BayoPest and PEST HP. And then under the hood, there's some multi-threaded things going on that makes it a little bit easier on the worker side to handle errors. So there's been some confusion around the differences between PEST and PEST++. So here I'm showing you the different file formats that you need for each one. So obviously these lists are exactly the same. And what that means is if your model is set up for PEST or PEST HP, your model is also set up for PEST++. And so this again is that complementary behavior that you can use all of PEST and all of PEST++ together once you get your model within that PEST model interface framework. Now, there's some purely optional things you can do with version 5 that deviate from PEST. You can add these so-called ++ arguments to the control file. And what those arguments do is they let you change the behavior of the algorithms within PEST++. All of the ++ arguments have internal defaults. So you only specify the ones you want to change. And the default values for all those arguments is listed both in the user's manual and it gets written to the rec file at runtime. In version 5, we've extended the name lengths up to 200 characters for parameters and observations. If you want to stick with 12 and 20, that's fine too. PEST++ can switch automatically between binary formats to accommodate that. And then there's this enhanced control file format that we've developed. Again, purely optional. You can use the standard control file as well. But this enhanced version, we needed that so that we start to bring a wider range of algorithms into the PEST world. So things we can't do just with ++ arguments. And so what we've done is we've consolidated all of the algorithmic controls in the PEST control file into one section, and we've given all of those variables internal defaults as well. So you only specify the ones you want to change, and you do that through keyword value pairs, kind of like Modflow 6. And we've also added support for CSV files. So those big, long sections of the PEST control file can now be put in external CSV files. And again, all this is described in the user's manual if you're interested. And now I'm going to let Mike talk about PyEMU.
Cool. Yeah, great introduction. And so, you may wonder why we have to talk about two tools at once. Well, PyEMU is basically an interface for the whole PEST family. It supports PEST++, but also PEST and PEST HP as well. And but it's using Python. Which gives you a lot of advantages for a kind of a programmatic approach to things. So similar to using batch files for people that are familiar with running some of the PEST utilities, with Python, you can do other things as well in the same context. So it has some advantages there. And originally, Jeremy started this project, the PyEMU, to sort of bring in some of the data worth and uncertainty quantification things that were already in PEST, but in a little bit more, just sort of a different way of approaching it, like maybe a little bit more efficient on the user side. But in the process of that, he also had to kind of be able to interact with control files and template and instruction files and things like that. And right away, people started to see the value of being able to do these things programmatically, not having to edit things by hand, but writing code to read and write all of those adjunct files. So basically, it's an interface into PEST and PEST++. It also can do some calculations on the outside. Can you hit the next one? Yeah, and at the end of the day, these things are complicated. There are a lot of options. There are a lot of different tools. And so there are a lot of opportunities to make mistakes. I mean, we never make mistakes, but some people may. No, there's always opportunities to make mistakes. And so trying to, the word automate is in quotes here, but sort of like pulling everything together in the entire workflow, hopefully going back to some of your original data sets. Maybe those are in Excel spreadsheets or tables that people have given you. And, basically pulling all of that stuff together for your observations, information on your parameters, information on the model, and all of those things. The more that you can kind of put that into a script that runs from start to finish, you decrease cognitive load, which is just this idea that you're trying to keep a million different subtle kind of unexciting details in your head all the time. Like if you can put those in a script, then you really have to work through it once, and then you can kind of re-engineer it as you need. It's more efficient, and definitely like reproducibility is a really important part of this. So next slide. And basically, this kind of automation, not only is it efficient, but it also can really increase dramatically sort of the rigor and the reproducibility of your work. And what I mean by that is, like, say you're given some data and you have to make a change to that data, like a unit conversion or something like that. If you have it in a script, you can make a note and say, I just changed this, by 2 orders of magnitude. And then later you might go back, say, why is that well at this funny rate? Well, you can see what you did. You can maybe change that decision. And so the kind of the paradigm shift from using like a graphical interface or a spreadsheet is that you're documenting every step of the way. And this decreases the redo despair. Like if you go back and you find a mistake, you don't have to try to remember this entire sequence of things that you were doing. And I like to think of this as a minimum viable product, kind of like from the agile world in software development. Like when I start a project now, I make a path from terrible data to a not very good working model to meaningless results really quickly. But that's just kind of working out all of these problems. And then along the way, you just start making improvements. You refine the data and you make sure it's working better. You work on the forward model and make sure that's working better. You start making decisions about which of these great features in PEST and +++ you're about to see that you want to use. But you've kind of like right away, you've got some of that plumbing. You've got some of that plumbing put together. And I just can't reiterate enough the value of being able to go back and have this documented workflow through the whole thing. Next slide, please. And so this is written in Python, as I mentioned, and a lot of people that use Python now use these tools called Jupyter Notebooks. So this is a screenshot actually from a web browser. So if you're not familiar with these notebooks, you basically get a combination of documentation, which is like this at the top where it says, let's quickly visualize model. But then right below that is executable code. And when you execute the code, in this case, it's just making a plot. But now, like, I have however much annotation I want to explain what I'm doing, and then the code that actually does the task and the results, like, this plot, all in one place in these notebooks. So it's a really great prototyping environment. And usually, like, a lot of people's workflows are kind of a combination of scripts that you run at the command line, not unlike, like a PEST utility or a model, and then these kind of notebooks where you have this interaction. So next one, please. And just another quick note to say that you're gonna hear in the next section quite a bit about ensemble methods, and there's a really great data analysis toolkit in Python called Pandas. It's very popular and very powerful, and so PyEMU takes advantage of Pandas to store a lot of the information that we have. So things like making these kind of plots of the whole ensemble of outputs, dealing with pest control files and all of these ensemble related files is really quite abbreviated once you learn Pandas. And I'm not going to lie, it's a little tricky to learn, but once you get over that hump, you have a lot of power at your fingertips. Next, please. And so, I mean, the main design philosophy is, this should all be easier. Like anybody who's been dealing with these kind of, with environmental models of any kind, there's a lot of putting square pegs in round holes. There's a lot of moving data around and trying to make things work together. And so taking advantage of a whole community within Python for all that data manipulation and management, and then connecting it directly to what you need to work with PEST is great. And it does make things easier. And it's object oriented, so you can be clever and advanced in your programming style and techniques. And it's an open development environment. So yeah, you can download the code, find mistakes or find things that you want to add and send them on up and be part of the community. Next, please. All right, so this started out with again, like a lot of the FOSSM, the first order, second moment uncertainty propagation work. Jeremy was motivated to bring that into this Python environment and try to make it hopefully a little bit easier for people. But one process of that is this idea of labeled linear algebra. So having matrices where you actually label the rows and columns, which is done in ASCII files in PEST, but being able to use that explicitly was quite a bit under the hood. But it brought some of these uncertainty tools into a really rapid framework. And again, interacting with the PEST control files. So this data frame, this pandas data frame method is a way that you can also list all of those tables. Effectively, they're tables of the parameter input information and the observation output information. So changing weights, changing bounds, changing values and things like that, or even names or whatever you want to do to manipulate those things is very easy through data frames. And then, as I said, there's a lot of support for ensembles, both getting them off the ground so that you can run them in PEST++, and then working with your results. All right, next one, please. So in addition to PEST control files, all of the PEST style files that John Doherty has been writing for years are supported in PyEMU. So you can read in results or intermediate files that are related to basically all of these different PEST utilities, which is very powerful. Also, there's geostatistics support for putting in pilot points in your parameterization. Tons of plotting options, covariance matrix, and getting your ensembles off the ground, and then this interface construction that we already talked about. All right, next. So one of the things that I'm the most excited about right now is this. It's something called PEST from, and Brioc Hemmings at GNS in New Zealand has been a driving force behind this. And basically, the idea is you want to be able to parameterize and interact with any model, right? There is a similar Python interface to ModFlow called FlowPy that's also pretty popular. So originally, Jeremy was working with that and took advantage of sort of this higher level interface into ModFlow. But we quickly realized, for one thing, ModFlow 6 changed a lot, and there are tons of other environmental models out there. So it seemed to make sense to generalize this as much as we can. And that's what's happening here. So basically, almost any environmental model that's like a groundwater surface water model is probably going to have some combination of array style inputs and outputs. So basically just, like basically matrices on a grid. List style kind of tabular type input and output. And so taking advantage of a lot of tools in Python and writing some general code within PyEMU was the ability to basically interact with both input and output to wrap around your model. So all the template files you need to write input, all the instruction files you need to read the output are sort of, you can make those generally for almost any model. One of the paradigm ideas here is to use a lot of multipliers for parameters. So you're probably, when you get to the point that you're using PEST and PEST++ on a model, you've got some kind of parameters already assigned because you're trying to get the model running. So rather than rebuilding it every time, you're actually running multipliers against those. And I'll show that in a second that gives you opportunities for this kind of nested spatial and temporal scales of those parameters, which is really cool. So going from the right, like a constant, like if you have a whole layer that you want to be able to change, maybe you have some zones that you want to change, Maybe some areas you really want to have pilot points to have more detail, or what's called grid scale parameters, where every cell in an area is its own parameter. Ensemble methods allow you to have those crazy numbers of parameters without the computational expense. And then this nested scale of parameterization allows you to kind of explore, it has a few advantages to kind of how you're running the algorithm. But once you get into to ensembles, you're always, and some of the uncertainty analysis, you're going to need like covariance matrices, often informed by geostatistics. So this set of tools also helps with that. All right, next, please. Yeah, so what do I mean by this multi-scale parameterization? I'll show an image in the next slide that'll hopefully make it pretty clear. But the idea is that, you know, almost always that kind of prior conception of a parameter field is coming from geologic knowledge and expert knowledge. We don't want to throw all that away and just take the mean or reduce it to just a couple zones or something. It's ideal if we can preserve that as a full dimensional prior. But then we need to be able to adjust using multipliers to adjust around that as needed in a history matching process to do a better job of matching the data. But if you only use, for example, grid parameters or pilot points, they don't change very much of that field. And so they may not be very sensitive and really won't change and be able to accept the information from the observations. So sometimes you want a really big knob, basically like a single value that changes that whole field up and down to kind of make sure that you're getting the mean in the right area. And then all of this kind of the pilot points and grid parameters and zones can work around that to help you to sort of help bring out some of the subtle changes that you need. And so this pulls out the uncertainty by scale, and then it can be useful to see when parameter compensation is happening. If you're seeing like a mean go to a really crazy place, for example. All right, next slide. So this is actually showing how this works. So on the left is like an original hydraulic conductivity field from a project we worked on together in Texas. And so then you can apply these various different levels of resolution. So we'll start in the third panel down is a global multiplier. So that's, again, this multiplier that's going to not change any of the pattern of that hydraulic conductivity field, but just move it up and down a little bit, which is basically just changing its mean. And then at the top, you can also add the pilot points. They're adding a little bit of variability, and then maybe some really pretty noisy looking stuff happening with the grid scale, right? But maybe there are places, individual parameters that can change and help a lot. But because these are all multipliers, you basically aggregate it all together at the end. And now when you look at the final panel at the bottom, it actually doesn't look terribly different. We've retained a lot of the characteristics of that prior mean that was probably expensive and people cared about, but we've given the model the flexibility to adjust at these multiple different scales. Super powerful. All right, next slide, please. Yeah, and so as I think Jeremy will discuss in PEST++, using some basic assumptions, you can have PEST++ generate an ensemble for you from parameters and bounds and some things like that. But a lot of times we know more about the system, maybe through geostatistics. So it's good to be able to make a prior covariance matrix and maybe sample that matrix for the ensemble generation. And so PyEMU has tools to be able to do that. Yeah, and I think I will turn it back over to Jeremy.
Awesome, thanks, Mike. Okay, so now I'm going to walk you through a workflow of using the PEST++ version 5 tools. And this workflow comes exactly from that USGS report that's still in press. So in this workflow demonstration, we're going to use one model in one PEST interface, and we're going to go through all these different tools just by changing the inputs in the PEST control file. So the synthetic model we're going to use is due to Freiberg. In this case, we're using a ModFlow 6 version of the Freiberg model that has 3 layers, and it's been made transient. We've also converted what was the river reach here running down the model domain into an SFR system so that we're basically routing flow down and out the model down here at SW1. We have pumping wells, we have recharge, and we have GHBs in this model. So in this case, even though Mike just talked about the benefits of using the PyEMU automated Python workflow, we're going to do this completely Python-less. And that's just to make sure we drive home the point that you don't have to use Python to use PEST++. And so what we're going to do is we're going to do some global sensitivity analysis to sort of check the plumbing and do some diagnostics. Then we're going to do uncertainty analysis and data assimilation. And then we're going to parlay those results in terms of a posterior ensemble into a risk-based management approach. So the PEST interface to apply all these different tools needs to be pretty comprehensive. And so we've set up a really big PEST interface with 8,000 parameters. How do you get to 8,000 parameters in a synthetic model? Well, you go grid scale, right? So we're basically, every model cell that's active has a parameter for HK, VK storage. The well pumping rates for all 6 wells across all stress periods are now parameters. Recharge is parameterized across stress periods. SFR conductance and GHBs are also treated as parameters. So we're going to use 2 different periods, even though it's one model run. We're going to have a historic period of 12 transient stress periods. And we're going to treat that as the historic period where we're going to do history matching. And then there's a forecast period after that. During that history matching, we're going to try to reproduce groundwater levels at GW1 and GW2, as well as surface water flow at SW1. So we have, some decent observations we're going to try to fit. And then we're going to try to make some forecasts. And those forecasts include these 3 quantities. We want to forecast the groundwater surface water exchange flux at the end of the historic period for the lower 20 reaches. We call that the tailwater. That should be a solution space forecast because it's at the end of the historic period. We just finished matching groundwater levels and surface water flows. So we should be able to say something meaningful with a little bit of variance about that exchange quantity. We also want to forecast the headwater surface water groundwater exchange, which would be these upper 20 reaches, but at the end of the forecast period. So that should be uninformed by our observations. We call that a null space forecast. And then we want to predict the groundwater level at location 3, which should be a mixed solution null space dependence. If you're unfamiliar with subspace terms and you want to learn more, there's some great webinars from John and Kath as part of the GMDSI project that talk about subspace concepts and spell it out really well. Okay, now this is a very important point and one that I can't stress enough. Those 3 quantities, those forecasts, are part of the PEST interface here. All right, we've gone through the effort to actually include those quantities as observations with 0 weight in the PEST control file. And that means as we move through all these different tools, we get to see how the forecast responds as part of the tool application. Instead of just seeing how we fit the past, we get to see what the forecasts are doing. And that's a fundamentally important exercise. And I realize you can't always make that happen. Maybe your forecasts come from a scenario model, but I would wager you could almost always add a stress period to the end of your model for the history period that has 20 years of time with less recharge to come up with some sort of output that captures the essence of the forecast, just so you can start to monitor those quantities as part of your analysis. Okay, so we need to come up with some observations for the synthetic model. And the way you usually do that is you pick a truth model and you use the outputs from that as the observations to then try to do history matching with. So in this case, we generated 300 realizations from a geostatistical prior. Like Mike said, with PyEMU, you can do it with PEST utilities as well. We ran those 300 and we picked an extreme realization with respect to the tailwater forecast. So we picked a realization that gave us a really small quantity of water moving from groundwater to surface water for those tailwater reaches. And that was because that becomes a hard forecast to hit, right? It's got an extreme mean value, but we just said it's in the solution space. So it should have a narrow posterior. So that becomes something hard to reproduce. And that's a good check on these algorithms. And like I said, we're going to use the outputs from this truth model as observations, like pretending like somebody went out and measured groundwater levels and surface water flows. And then we're also going to have true forecast values as the answer at the back of the book. Now, you don't always have true forecast values, but in this case, we do just for demonstration purposes. Okay, so you've gone through the process of setting up your model for PEST. What's the first thing you want to do? Well, you want to check the plumbing, right? You want to make sure mechanically and conceptually the PEST interface is running the model like you would expect it to do. A great way to do that, I think, is with global sensitivity analysis using the method of Morse. So this tool, PEST PPSEN, implements the method of Morse. The Morse samples parameters across parameter space along these trajectories. Here, that's a 2-dimensional space with 3 trajectories, and B, that's a 3-dimensional space with 5 trajectories. But at the end of the day, what happens is you get a mean and a standard deviation of the parameter sensitivity to all the observations in the control file. Now, why this is important is because we've included those forecasts. So not only do we get the mean and standard deviation sensitivity to the past for history matching, but we get to look at how the forecasts are affected by the parameters. What are the important parameters for the forecast? So the way we're going to do this, we're going to make one change to the pest control file, and that is this tie by group option. Tie by group drastically reduces the number of parameters by treating every parameter in every group as one parameter. So all those HKs in layer 1 for every model cell are going to function as one parameter. Now, I don't recommend this for data assimilation uncertainty analysis for obvious reasons, but for this screening level tool, it's a great way to cut the number of runs, but still get some sort of insights and do some diagnostics around the model. So it takes the model 52 runs across our 12 parameter groups. And when you do that, you can make plots like this. This would be a measure of the mean sensitivity of these parameter groups on the bottom to the 4 quantities output from the model we're interested in. The objective function, which sort of represents our ability to reproduce the past, as well as our 3 forecasts. And so what we see immediately, what's important for predicting the past is HK layer 3, a little bit of recharge, a little bit of well extraction parameters. But what's important for the forecast is almost entirely based on forcings. Now, I won't get into the subtleties and sort of say something nasty about how everybody obsesses with HK, but I think it's clear here that what's important for the past isn't always what's important for the future, right? Okay, so in addition to that mean though, we get to understand how that sensitivity varies across parameter space. And that's what this plot is, represented as a coefficient of variation. So we see that the relationship between HK layer 3 and the objective function varies quite a bit across parameter space. That indicates that there's probably a nonlinear inverse problem at play here. And there's less variability in the relationship between the forcing parameters and the forecasts of interest. But conceptually, this all makes sense. So we've run the model 52 times, things seem to be working right. So then you want to step up to the next level of analysis. And in this case, we're going to do some data assimilation and some uncertainty analysis. And we're going to do it first with a code called PEST GLM. This is the code formerly known as PEST++. It implements regularized Gauss-Levenberg Marquardt with automated SVD assist. But the focus on uncertainty in PEST GLM is twofold. One is you can do automated FOSSum parameter and uncertainty and forecast uncertainty estimation every iteration. That would be like a PREDUNC1 workflow. It happens for free every GLM iteration. And you can also do what we call Bayes linear or linear assisted Monte Carlo every iteration and at the termination of iterations. And so that Monte Carlo workflow is nice because it's a more nonlinear type of uncertainty analysis. So you can essentially get 2 measures of uncertainty from this one tool. So how are we going to apply this tool? Well, we still need to reduce the dimensionality of the parameter space some because we don't want to run the model 8,000 times to fill a Jacobian. So what we're going to do, we're going to use just the PEST control file interface to tie parameters that are spatially distributed into blocks of 6 by 6. Now, this is suboptimal compared to pilot points, which give you a smoothly varying field, but it's a nice clean interface for this demonstration problem and lets us still express some heterogeneity. So that cuts our number of parameters down to 330. We're going to use the automated SVD assist thing to cut parameters further, and then we're going to do 200 posterior realizations at the end. So you simply call PEST GLM on this problem. Once you have your control file modified, it takes 682 model runs, and you can do some cool things with it. So the first thing most people want to do is plot observed versus simulated. So simulated best fit in the red are the observations, on top is the surface water flows, and then the 2 groundwater locations below it. I think that's incredibly boring and also ignores all we've been talking about. You can look at some CSV files, the GLM rights, and you can make these plots. They're actually from that report that's press. We have a red line, but now we have lots of blue traces. That's the Monte Carlo results from those Monte Carlo runs. Again, we'll run in parallel. But more fitting the past, let's look at our 4. Those are down here at the bottom in E, F, and G. And we get 2 measures of uncertainty, like I said. The smooth Gaussian distributions, those are the FOSSum estimates. And then the blue histograms are the Monte Carlo results. The red vertical line on each one of those, that's the true value. And so what we want to see is that the posterior covers the true value. And in all cases, we have done that. So we haven't done everything wrong. And we can also see that null space solution space dependence, right? The forecast, the headwater forecast, prior and posterior are nearly the same. The tailwater forecast is much more peaked and narrow, so it's a solution space thing. And then the groundwater level forecast is sort of a mixed bag on that in that sense. We should also look at parameters as part of this process. Here's the minimum error variance parameter vector. You can see now that blocky pattern that we got from tying the parameters together in groups of 6 by 6. This is a heavily regularized solution, but it fits the data pretty well. We can also plot up one of the 200 posterior realizations. This is what they look like. Again, very blocky, but consistent with the prior, and it reproduces the historic observations. So we would call this a member of the posterior. Sweet. Now there's another way with PEST++ to do data assimilation and uncertainty analysis, and that's with PEST PPIES. There's a previous webinar on ensemble methods, so I won't get into that. But again, the focus on uncertainty here is the fact that it's an ensemble method, so the fundamental unit of operation is the ensemble. So you have to embrace uncertainty to use this tool. So for this application, we're going to use all 8,000 parameters. We're going to use a geostatistically correlated prior ensemble that was generated with PyEMU, but you can also generate that with the PEST utilities. We're going to do a little bit of temporal localization. We're going to do some automatic adaptive localization. If you want to learn about those, again, see that previous webinar or wait for the USGS report to come out. But it takes 378 runs for this tool, and we can make very similar plots, except now we have gray distributions across all the plots, and that's because as part of its operation, PEST PPIs has to run the prior ensemble. So we have those prior outputs as well. And again, we can see down here, the posterior histograms all bracket or cover the truth, which means we haven't done everything wrong. And again, we can see that solution space, null space variability across the 3 forecasts. Cool. So we can look at parameter fields. Now we see that cell by cell variability. This would be, we call this the base realization in the IES world. This is as close as you're going to get to a minimum error variance solution with an ensemble method. It's more or less regularized, and it's consistent with the prior in terms of its variability. We can also look at stochastic realizations. A lot more variability, cell by cell variability, but again, the spatial patterns of variability are consistent with the prior in a geostatistical sense, and it reproduces historic observations. So again, we would call this a member of the posterior. Okay, so at this point in most modeling analyses, right, we're going to do some scenarios, right? We would run the model forward with more pumping or maybe a new extraction well, and we would monitor outputs of interest, hope the results are acceptable. Maybe, the concentration at the compliance point is low enough, or the surface water groundwater exchange stays high enough that we maintain ecological flows, and then we cross the finish line, right? Here we are crossing the finish line. But really, if we think critically about this, we're really not doing ourselves justice after all the sophistication we've applied to just run a few sort of what-if scenarios, right? The idea of acceptable, right? It means the simulated forecast values are acceptable to the decision makers. And that means we've essentially avoided a bad outcome, which means acceptable really is what we would call a feasible solution, right? But in the management optimization world, feasible solutions are usually not necessarily the optimal solution. Whereas optimality, what that implies is there's a better way to manage the system, where better means save or make money while ensuring a bad thing doesn't happen, right? And so ultimately what we want to do is we want to use management optimization techniques to do better with the scenario piece of our modeling workflows, right? And what really happens is we can now frame the results in terms of dollars and risk. And again, risk implies uncertainty. So this is where uncertainty sort of propagates through this workflow. So if we're going to talk about management optimization, we should talk about a little bit of terminology, right? We've talked a lot about parameters, whereas parameters are the inputs to the model that are uncertain, that we want to account for and adjust and propagate through. We now talk about decision variables in management optimization. And decision variables are the inputs to the model that we have some control over, that we can adjust. So pumping rates, gate operations, etc. But the big link, and this is the fun link that I like, is what was a forecast or a prediction in the UQ data assimilation world now becomes a model-based constraint in management optimization. It's fundamentally the same thing. It's still an output from the model. It's something we haven't measured. But the difference being, when we move to management optimization, we have to elicit values from the stakeholders and decision makers. What is exactly the bad thing that's related to this model output? What value should we avoid and stay above or below to make sure a bad thing doesn't happen? And just like forecasts and predictions are uncertain, model-based constraints are uncertain. Cool. So how do we deal with this uncertainty? Well, we estimate the uncertainty in model-based constraints in exactly the same way we estimate uncertainty in forecasts, right? We can use FOSSM or we can use ensembles, but now we're going to employ this concept of risk. And risk lets us collapse that uncertainty to a single value, but that single value implicitly includes the uncertainty in that underlying constraint. What do I mean by that? Well, let's talk about a hypothetical dewatering problem, right? Let's say we're at a mine or at a construction site and we need the water level to be 19 or less. So we build a model and we ask the model, what's the water level here? Is it 19 or less? And so in an optimization setting, we would want to make the water level exactly 19. And that's what we're showing here in the middle for risk neutral. But the reason being, if we're more than 19, we can't proceed with our activities. If we're less than 19, we're spending too much money on dewatering, right? So the goal of the optimization program is to adjust the dewatering scheme until the water level is exactly 19. But you can see there's a distribution around this 19, and that's because we have to use the model to simulate the relationship between the dewatering and the simulated water level. And so most decision makers are going to be risk averse in this setting, especially when they're wanting to do planning to move towards cost benefit analysis. And so what they would say is, I want to be really sure that this dewatering system is going to give me 19 or less. And so what we do, we tell the model, actually the constraint value is closer to 13, much less than 19. But given the shape of this distribution, that puts us at a 0.95 or a 95th quantile of the distribution at 19. So in essence, we're 95% confident the water level will be 19 or less, that we're going to satisfy that constraint. And so that's essentially how we use risk and uncertainty to still feed forward into an optimization solution to get one answer, but that one answer then carries the uncertainty with it implicitly. Now, these are nice, smooth Gaussian distributions because they come from these equations, right, from FOSSM, where we estimate variances. But if you're using ensembles, there's another way to do this same operation, and that's called stack-based optimization. So in this case, we use the actual shape of the probability distribution for the simulated water level. We do the same risk shifting operation, except now it's non-parametric. So we relax the assumptions a little bit. So we're now going to use a tool called PEST PPOpt. It's the first member of the PEST++ suite into the management optimization world. It won't be the last. There's a few under development currently. This tool implements linear programming with chance constraints, so it's applicable to mildly nonlinear relationships between decision variables and constraints. We use all that same parallel machinery to fill the response matrix, which is synonymous with the Jacobian. And of course, we have seamless integration with FOSSM and stack-based chance constraints for the optimization under uncertainty piece. So what do we have to do to apply PEST PPOpt? Well, we're just going to make changes to the control file. And what we're going to do is we're going to treat all those well flux parameters now as decision variables, right? So it gives us 144 decision variables where we're going to try to optimize the pumping rate over that 24-month transient window so that we get the maximum amount of water out of the system while avoiding bad ecological outcomes. So what are we going to do? Well, we're going to add some prior information equations to the PEST control file to say every stress period, we need at least 750 cubic feet per day as a combined rate from these 6 wells. I don't care what 6 wells you have to pump, but I need 750. And that would be for some sort of nearby beneficial use maybe. But at the same time, we want to make sure we maintain some sort of base flow to the surface water system. So for both headwater and tailwater reaches, for all 24 stress periods, we want to maintain 250 cubic feet per day as a minimum. And just like those were forecast before, they're uncertain now as constraints. So this is where the chance constraint process comes in, is around those headwater, surface water, groundwater exchange constraints. So we're going to do 3 runs. We're going to do a risk neutral, a risk averse with FOSSM, and a risk averse with stacks. In the stack-based one, this is where it gets really cool, right? We take the posterior parameter ensemble from our previous analysis, and we simply supply that to PEST PPOpt and say, use this as the stack. So there's a really nice linkage in that workflow of moving from what is UQ and parameter estimation and data assimilation to risk-based management optimization. So here's a few options we add to the PEST control file. It takes less than 200 runs for each of these. But then you can make plots like this. I really like this plot. I hope everybody else does too. I spent a long time making it. But this plot, what we're showing here on the left axis is the pumping rate of each of the 6 pumping wells. The bar here is color-coded to the well location over here on the right. So you can see during the wet season, we're full on, right? All the pumping wells are at maximum capacity. But as the dry season comes on, this shows you the optimal pattern of using those wells to keep extracting the maximum amount of water while maintaining those ecological flows. Right, and you can see in the depth of the dry season, we get exactly our minimum of 750 here on this red dashed line. And then as we move down from risk neutral to risk averse types, the length of that time of getting just the minimum grows because that's the cost of uncertainty, right? We have to hedge against those unwanted ecological outcomes. So we have to leave more water in the system to discharge to surface water. We can also look at this on the constraint side. So this would be the headwater and tailwater, surface water, groundwater exchange fluxes. We need at least 250. So the red dashed line is what we have to be above. And in the risk neutral setting, the optimization algorithm works as expected. It takes it right to 250 and keeps it there. So we're getting optimal amounts of water out of the system while maintaining that 250. But as we start to consider uncertainty, we have to leave more and more water in the system. So in these lower plots, we have to stay off of that 250 so that we leave more water to make sure we keep at least 250 going, because we don't know exactly what the surface water groundwater exchange flux is going to be. Okay, I think Mike is up. Mike, are you muted?
Yeah, okay. I think I'm off mute. All right, cool.
Sweet.
Well, so as you saw, you know, one of the important things I want to drive home again is back to the control file and how this is all set up. That if you have a pest control file that you've built for PEST++, you can run it in PEST HP, and if you have it in PEST HP, you can run it in like wrapping up the model. Once you've created this interface around your model, everything you just saw, with the exception of adding a few plus options here and there, is available to you just by changing which executable you run for the most part, and maybe making a couple little changes. So, and so we've gotten a start on a GitHub repository here of just workflows for PEST++ within PyEMU. There's only a couple there right now, although I'm great, because the first notebook shows programmatically how do you set up one PEST++ interface using this PEST from functionality I talked about earlier. And then the first thing that's often really good to do is just run a Monte Carlo. You know, run Monte Carlo and see how you're doing. See whether you're likely, whether the distributions you get of observations are even likely to overlap with the true values or your observed values or not. Because if you may as well figure out why before you go too far, because the prior Monte Carlo is going to be sampling the variability out to the bounds, and if you're not hitting your observations, history matching probably isn't going to get you there. So I'd keep your eye on this spot, and there will be links provided after the webinar as well. But so this is going to be a growing repository, and you can certainly contribute one if you want. So let's just walk through the setting up the interface first. So next slide, please. This is just to show kind of, and if you don't know Python, hopefully will not turn you off too bad, because the idea is pretty like wordy. And by wordy, I mean, we're kind of describing things using words, and it's really not that hard to follow and get your head around. But so the very first thing that you do if you want to make an interface around a model is pass. And so the arguments here that you provide, this is sort of the bare bones, but you have an original directory. So that's just a directory that contains all your model files. And then you have a new directory. The first thing it's going to do is just copy that over and make a new directory for you. Remove existing true means if you've been messing around and making mistakes and populating that thing with garbage, it'll start over for you. It won't, but it'll make a new copy of the new directory. So long names equals true means that pest from is going to cram a lot of useful metadata into your names for parameters and observations. For example, parameters are going to say like which package and if you have layers and rows and columns and things like that, which of those are in that one parameter, so that you can parse it for plotting. And then for observations, it'll try to put in things like time and location. Spatial, you just have to basically, if you have, you know, your model must be on a grid, right? There are a couple ways to register that grid to actual space. It's basically the corner and the spacing and a couple other things. And then start date time is allowing you to, for all that metadata, you'll be moving through time, but it'll know where it started. All right, next, please. Right, so now this is a great example of saying that you want to create observations of streamflow routing from a ModFlow model. So you pass it a CSV file. Because it's a tabulated file, all you really have to say is this use calls argument that's saying I want to observe gauge number 1, the headwater and the tailwater, and then the index is going to be times. And so basically that's all you need to do to register the CSV file, and then you can give it an instruction file name. And so not only will it create the instruction file, it will also populate this object with all the information you need in your pest control file for observation names and the output and instruction files, so that eventually you can just write it out. All right, next slide. All right, so now for parameters, you have a ton of choices here, and I won't go into all the. If, for example, recharge varies over time, right? You may want to have like a multiplier on the entire recharge array, but at each time to account for maybe if you're using an external recharge model, it may be biased or have some errors in the climate driver. But you also might have like a zonal variability, or even like you want to use pilot points that maybe those don't change over time, but they do change over space. And so you can mix these together, which is pretty amazing to me. And then because remember, these are multipliers. When we set a bound, those bounds are like 0.8 and 1.2 here. It's just like saying that multiplier can go up or down by 20%, roughly. If we're using pilot points, you can pass it a geostruct, which is going to give you the varigram information needed for the interpolation points. Here, but you can also pass an array of where the pilot points are active, and there was something else I was going to say. Oh yeah, and the spacing. So you can decide like how frequent, how many pilot points you want in your area, and that's it. Boom, pilot point network. Next slide. And so here, maybe you want to have, as you saw, there's some motivation for having grid-based parameters, where you have a different parameter for every model cell. So here you're passing very similar arguments, but you're saying the par type is grid instead of pilot points, which it was before. And then some like a par name base. So every parameter is going to start with HK1_GR. So you know it's a grid. You can assign it to the group. Here, the zone array is that active area being shown. And actually, in this case, the par style being direct means if you want for some parameters to not use a multiplier, but actually use the base value, you can do that too. The geostruct is super important when you're using grid parameters, though. So you definitely need to put a little bit of thought into that. But so now with this setup, we would have some observations of outputs from the Streamflow routing package, and we've parameterized inputs at various scales. So next one. So also kind of amazingly, this pest from all that plus or pest end up calling. It'll be a Python script that uses some of the PyEMU functionality, for example, for broadcasting or interpolating your pilot points, or doing some other pre-processing. Applying all of those multipliers is actually, there's a lot going on there. So and that's all done for you. But you can add things too. So for example, pest from doesn't know what the model command line is. So you can append that, which is this first line here saying we want to run MF6. And then you can build, now you've got all this information that you need to create a pest control file. You have parameter information, observation information, input and output files, a run script. And so now when you say builds pest, it's going to create a pest control file for you, and then you can write it out. You can also do some of that pre-population of covariances and ensembles, like we talked about before, with a few more command line arguments. So next. So one of the crazy good things about this is, for example, I would say as modelers, we tend to get pretty tied to the resolution, like the grid spacing of a model, because there's so much work that often goes into, for example, I mean, placing wells is pretty easy, but creating a stream flow routing network can be quite a tedious task. And recharge and all these other things, and making sure they're on the right thing. Well, if you're using, for example, if you're using a mod flow model and you're using FlowPy, you can actually just change a few assumptions and rebuild the entire model with a different grid. So now suddenly you could change to a finer grid, or say you think you could get away with a coarser grid with its accompanying faster runtime, and you don't even have to change that PEST from script at all. If you, as long as arguments, in the example here we don't, then you could, once you've built the new model, if you want to do it by hand, great. I'd recommend using something like FlowPy. But then now you can just reparameterize the entire model and do your whole uncertainty analysis with a new resolution. So it's really powerful. All right, next slide. And this is just showing that once you've set up what we just showed, basically that would be your entire. And take a look here. And this is looking now, comparing two different resolutions of the model. So the top plot there, at the lower resolution, we probably don't have enough detail to actually get the dynamics of these observations. But once you increase the resolution, now you're actually getting enough. So so highly motivated to do that. And next slide. And now this is just showing now, taking that out to the forecast and seeing the variability that we get with the two different resolutions of model. So I think that not only the reproducibility, but this ability to really change a lot of things on the fly is a really powerful part of this this tool set. Back to you, Jeremy.
Awesome. Thanks, Mike. So I'm going to really quickly go through some near-term things that are coming up with PEST++ and PyEMU. So first off, we're going to start to try to offload some solution calculations to workers. I know that's a completely new run management paradigm, but it's something we need to do very high dimensional localization calculations. And we're also starting to plan and lay out what would be a C++ geostats engine. And we're going to use that to try to automate some of this geostatistical prior ensemble generation, hopefully under the hood with PEST PPIS and other tools to save you that extra step. There's a few tools in development. One of those is PEST PPDA for data assimilation. This is being led by Ayman Alziri at USGS. I'm pretty excited about this tool. It's going to bring, for the first time, sequential recursive type of estimation. So iterative ensemble Kalman filter to the PEST world. And so that means now we can start to do these forward in time processes maybe a little bit better for things like subsidence and mass transport and saltwater intrusion, as well as operational groundwater modeling. So we're pretty excited about that. Zach Stanko is developing a constrained multi-objective optimization tool. So looking at evolutionary genetic global algorithms with multiple objectives, but of course those will include chance objectives and chance constraints, so still fossums and stacks. That'll be ready pretty soon. And last but not least, Matt Knowling is developing what I think will be an industrial strength constrained nonlinear optimization tool. So using ensemble approximations combined with constrained quasi-Newton, and of course fossum and stacks throughout. So look for those in the near future. And then on the PyEMU front, again, we realize not everybody's a Pythonista. So we're thinking about now, how can we zoom up this PST from to even a higher level? So maybe spreadsheet driven or YAML JSON driven or even GUI driven. And we realize we need better support for unstructured grids. We're working on that. And of course, the geostats that are in PyEMU now, while they function appropriately, they're incredibly slow. So we're hoping to speed that up with that C++ engine, no doubt. So if you're interested in any of the tools we talked about today or the codes, this is where you can find all those. They're all on GitHub. And like I said, that Impress USGS report hopefully will be out soon. And thanks for listening. And we'll take Any questions or comments? I think we're back to Kath now.
Hi, yeah, thanks, Jeremy and Mike. That was really excellent. There are two ways that we're able to take questions. One, if you put your hand, if you click on the hand icon, we can take your questions directly, or otherwise just type them into the Q&A window. Hang on a second. So there is one question already from Stuart Brown. And it's, is there or are we likely to see support in the future for unstructured grids?
Yes, I would say most definitely. And I realize we've shied away from that for a long time with both PyEMU and PEST++ tools, just because I'm a little bit scared of unstructured grids, but I think the time is right now to sort of get into that space. So that's definitely on my agenda for the next few months as well.
Okay, that's good. That's good for all of us ModFlow 6 newbies.
Actually, can I make a quick plug though? So I think an sometimes overlooked feature of ModFlow 6, for all you ModFlow fans out there, is that the local grid refinement, so having two models at different resolutions, is super efficient now. And so I think a lot of times if you want to, I mean, I know there are tons of really good applications where an unstructured grid is the right thing to do, but there are definitely times where you can resolve around like an area of interest at a higher resolution and have a lower resolution outside, but they're both completely structured and treated as two models, but then they run really quickly together. So that's another option to consider.
Nice.
We just had another question actually from the chat room asking about unstructured grid again with FeeFlow and FEM users, but we've covered that.
Oops, we lost Kath.
Sorry. Just having a bit of trouble seeing these questions. Oh, sorry, another one from Stuart Brown. With IES, say you have an ensemble of 80 realizations, how many would you run in parallel, or all 80 if you could?
Yeah, I mean,
when you're running the ensemble, every iteration you run all of them. Oh, sorry, Jeremy.
Yeah, I was going to say, I mean, the stuff is so embarrassingly parallel that if you have 80 computers, then yeah, run all 80 at once just to save yourself the time. But again, I mean, it comes down to what sort of resources you have available. But essentially, every iteration, the whole ensemble has to be run. That's the nature of the algorithm.
Cool. Okay. Sorry, there's a bit of user error here. The questions are okay. This might be better. Some of these questions I'm unable to see fully. There's a question here from Bezard, but I'm unable to read the whole question, Bezard, at the moment. If you wanted to put your hand up, you could ask it directly. Or alternatively, are you, Mike and Jeremy, are you able to see the full questions?
I'm trying to see it.
Okay. So Bezard's just thanking you for your presentation. So
okay.
See that now. Okay. So Bezard's asking, are there any training videos for PEST++?
I think we just had one. No, I mean, I mean, I've thought more about making some videos for both PyEMU and PEST++ that are a little more granular and sort of like bite-sized of like different topics. And so I think, again, if that's something people are interested in, that would give me some motivation to start to work on some of those.
Okay, cool. Okay, there's a lot of questions actually coming in through the chat window, so I'll just go through those now. Winnie Timms asks, the testing the grid resolution is useful. Is it also possible to test the resolution of layers, for example, the number of layers within alluvium? Mike or Jeremy?
You'd have to do a little bit more modification of the PEST from stuff, because a lot of that is going to be based on a single array, but it wouldn't be very hard though. And I'd also make a plug. One of the links at the end is something called ModFlow Setup that one of our colleagues, Andy Leaf, has made, and it does a lot of the geospatial processing of, say, giving it, you can provide files for example, like the bottom of the alluvium, and then tell it how many layers you want it to divide it into, and set the spatial resolution and stuff. Once you rebuild it, you'd have to do a few minor modifications to the PyEMU stuff, but in principle, absolutely, you could do that quite efficiently.
Okay, question from Louis. Some of your applications showed us that you showed were done in standard computing, or did you use cloud computing?
Yeah, that's a good question. So I did all this on my computer locally, just because it's a fast running synthetic model. But I know Chris Nickel, for example, has used the PEST++ tools in a cloud environment. I think other people have as well. So it's totally possible. And that run manager, again, being TCP/IP based, should be sort of seamless running. If you wanted to run the master in your local machine and start workers in the cloud, that should, quote unquote, should work, right?
Okay. I'm just going back and forth because there's quite a few questions in chat, and this is exceeding my ability to negotiate this screen. Hang on. When you use PEST from, and this is from Tao, when you use PEST from to generate many multiplier parameters, how do you justify the bounds of those parameters? Mike or Jeremy?
Yeah, I can take that. I didn't want to interrupt Jeremy. So hi, Tao. So when basically you can set an ultimate upper bound and an ultimate lower bound to make sure that as you're multiplying multiple, this is crazy, multiplying multiple multipliers together, right? You see your question, that they could expand out to some really extreme value. So right now, the main way to deal with that is to cap it. One thing we've been talking about is making that cap maybe be zone-based or lithology-based. Right now, it's just for the whole array. But yeah, it's a great question though, because you can get extreme values when you're using multipliers.
Yeah, and I would add, there's a really good paper from Sean McKenna and others just this last year where they talk about doing this multi-scale parameterization and sort of apportioning prior uncertainty amongst the scales, so that you would expect a lot of uncertainty at the grid scale, but maybe not as much in the mean, because you don't think the mean's probably going to move as much, or maybe you do think it's. And so there's some justification in that manuscript about sort of setting up this multiply. There's multiple scales of multipliers and attributing prior uncertainties across those.
Cool. Okay. I think that is the extent of the written questions I can see at the moment, unless you can see others. Oh, hang on. There's a new.
I can see one.
Yeah.
Somebody is asking, are there any case studies and examples where PEST is used with MF6 for parameter estimation, risk, and uncertainty? Examples to learn from. Please give some references. So as part of PEST++ version 5, there's a benchmarks folder on GitHub. And inside that benchmarks folder, there's an MF6 Freiburg directory. And in there is where all the files that were used to generate these plots today are located. So like all the PEST interfaces for those, global sensitivity analysis and data assimilation and uncertainty and optimization, that's all in that folder within the PEST++ repo. So, I mean, that's a basic sort of, straight ModFlow 6 example without any pre and post processors, but maybe you can get the gist of what's going on from that.
There's another one. Is PEST-IS able to handle posterior distributions that end up being multimodal, or if in general all ensembles move forward towards the same minimum of the objective function?
Yeah, so that's a really tricky question. So PEST-PPIS is formulated on the same assumptions that PEST and PEST-PPGLM use. That we have, a Gaussian posterior. So in theory, it can't do that, but there has been some evidence that it can, handle with multiple minima because of the way the ensemble covers parameter space. So instead of, doing a localized gradient calculation, it's approximating the gradient over a larger region. So it can crawl through some local minima and move towards a global minima. But if it truly is a multimodal system, then yeah, I mean, you're sort of, I think you would have a hard time with that with PEST-PPIS.
Jeremy, can you see any new questions? Sorry.
Yeah, but I'm going to give this one to Mike. Okay. How does a modeler explain observations that fall outside of the confidence limits of prediction, e.g. modeling COVID numbers in Melbourne?
Right. Well, that's right. The reason that happens is that there's one of two answers to that. Either the observations are not what you think they are, and so the fact that they're falling outside of your confidence limits means that the observation isn't right, or so maybe someone's, those aren't real COVID numbers. That I doubt that's the case, right? So the other reason is that there's some behavior or some characteristic of the model that isn't operating properly, that isn't properly constrained or represented. So for example, college students and university students returning and going to lots of parties in my state of Wisconsin made COVID numbers go up a lot more than modeled, right? Mm-hmm. And so actually there's a cool tool if you're using ensemble methods. You can run prior Monte Carlo and you'll get bounds on all of your observation, like your outputs from the model, and you can compare that to the true observations. And if they don't overlap, if your true values are outside of your confidence limits, that's a really good opportunity to explore both the quality of the data and the characteristics of the model and try to find out why is that misfit there. And Jeremy and I have a slightly different view of this sometimes. He's sometimes slightly more cavalier and put in a little switch that just says, assign all of those 0 weight and keep going, which is a good thing to do to get off the ground. But I also think that getting that report out and looking at which of those observations are not matching is a great opportunity to figure out what's wrong with the model or the observations. Mm.
Okay, I don't see any more questions in the Q&A. Is that your reading of the Q&A box? And I'll just go to the chat box. I think that's also the case. So that's good. All right. Okay. Thank you both very much. Excellent presentation. The presentation will be on the website for those of you who want to watch it again, or if people have missed it that you want to recommend watch it, they can go to the GMDSI website and we'll be able to click on this presentation, probably not today, but by tomorrow, all going well. And also there'll be a link to the slides at the same website. Also the links that that Jeremy and Mike mentioned to the PEST++ and PyEMU GitHub sites will be on the resource page of the GMDSI website. Today, one thing that we heard quite a lot about was the importance of the prior parameter distribution, and that's based on geological inference, and it feeds into uncertainty analysis and optimization. And this is very good. But there's often a lot of questions, not so much today, but a lot of questions have come up in previous webinars of how do you derive that prior in practice. And this question and other issues are going to be addressed in the next webinar, which is looking at these relationships between hydrogeological knowledge and numerical models, and also the relationship between hydrogeologists and modelers. And we're privileged to have Wendy Timms, Chris Nichols, Rick Evans, and Hugh Millimus who'll be talking on this topic. So at this point, I think I'll just end the webinar, and again, thank Jeremy and Mike very much, and feel free to contact them through the GitHub sites too if you want to ask more questions. Great, thank you.